This module, well, talks about the solution to the acid-base equilibria homework number 4. Just because it's quicker to put up a little video than it is to type out all those equations in Canvas. So this is a problem, percent dissociation of a solution of nitrous acid, 0.07 molar, when you add 0.082 grams of sodium nitrate to it. And I give you the Ka for nitrous acid. This is the common ion effect type of problem. Percent dissociation will be the concentration of hydrogen ion at equilibrium divided by the initial concentration of nitrous acid times 100. So what we're going to do basically is set up two ice tables. One initially to find out the concentration of every species in solution in the nitrous acid solution before we add the sodium nitrate, and then we're going to add the sodium nitrate and see how the equilibrium shifts with another ice table. So first ice table looks like this, and I get my x equal 0.00513. I think the other root was negative, so we discarded it. And by the way, 5% rule wasn't satisfied here, so just solve the quadratic formula. Next, we're going to add the common ion, nitrite. So first we figure out how many moles of sodium nitrite we added, just the mass divided by the molar mass, and then we find the concentration by dividing the moles by the volume, 115 milliliters. And that's the concentration of nitrite that we add. And then, okay, because we already had some in solution from our dissociation of nitrous acid, we add these two together to get our initial concentration of nitrite for our second ice table. And our initial concentration of nitrous acid we got by just subtracting basically our x from our first ice table from our initial concentration of nitrous acid. And we get this guy. So now our second ice table. These are our initial concentrations: nitrous acid, hydrogen ion, nitrite. This is more than this because we added the sodium nitrite. And the sodium is just a counter ion. It dissociates completely in water, and sodium doesn't do anything else. Anyway, so there are our equilibrium concentrations in terms of x. Put it into our equilibrium constant expression, and if you neglect x compared to this, you get an answer that's pretty close. It satisfies barely the 5% rule. I didn't though, I just solved the whole thing. Anyway, I got my x equals to this. And let's see, the other root I think was too big. It was bigger than this number. So we discarded that. And so now our concentration of hydrogen ion at equilibrium will be what we started with from our first ice table minus what we lost after we added the nitrite. And there is our equilibrium concentration of hydrogen ion divided by the initial concentration of nitrous acid times 100, and we get 3.1%.